we are going to talk about biological passive and active channel models. So let's start with the passive channel model.
Hi everyone. So the first circuit that we'll be discussing is the passive channel circuit. Here basically we have an FGOTA whose positive terminal has the input and the negative terminal has a reference voltage, which in this case we have given as 1 volt. On the output we have a FG switch connected, which is basically a floating gate PMOS, and which is programmed through its I bias. In the output we have an OTA buffer, which is basically used to improve the quality of the output that we get. The final output that we get from this circuit is the membrane voltage. So in this case, as I've already stated, V reference has been given as 1 volt, and we give various DC values to the input voltage starting from 700 millivolts going up to 2 volts. So what we got as output will be explained by my friend Praneet.
If you can zoom in, this is the XCOS block diagram for the passive channel circuit. It's just a simple OTA connected to an FG PFET switch. So the output connected here is measured using an IO buff 3, which is basically a buffer, and then measuring the output for the passive channel circuit. And what we observed is whenever we gave an input which is more than the reference voltage, we got an output that is, like as you can see, more than the 0 voltage. We have given DC voltage of different values, and finally when the input was more than the reference voltage, that is 1 volts, we got an output. These are the different this is the same passive channel output for different values of I bias. As you can see, the I bias for this FGOTA for this output diagram is 10 microamperes, and for the I bias for the switch is 1 microamperes. It follows the same circuit even for the next diagram. Try to change the I bias values and try to measure the output. So here we have decreased the FGOTA I bias to 5 microamperes, and the FG switch is 1 microamperes. So what we found is the output just gives a little rise in the voltage.
Gating circuit. This circuit effectively is an FGOTA connected in a voltage follower configuration, and this behaves as a low pass filter. As such, the output values follow the input. So here the V membrane is the input, and the negative terminal is connected to the output as a feedback. So effectively the output voltage follows the input voltage, and by varying the I bias values of the FGOTA, we can affect the output values to some extent. So the output of this circuit will be explained by my friend Kuppa.
Potassium channel gating. As you can see, it is just an FGOTA in which the negative terminal is connected to its output. So the expected output should be a low pass filter, that is the output following the input with a slight delay. And that is exactly what we found out, that we observed. And what happened was, initially we got the peak to peak voltage of the output as 1 volts, but by varying the I bias of the FGOTA, we could lift it up to 1.5 volts. So finally we found out our VK as 1.5 volts. I bias values that we got for these were: I bias for the FGOTA was 1 microampere, the P bias for the FGOTA was 10 nanoamperes, and the N bias for the same was 10 microamperes.
Sodium channel gating circuit. In this circuit we have an FGOTA which has a feedback from output to the negative input through an FG switch, which is basically a floating gate PFET with its gate connected to the ground. We bias this PFET using the I bias current. So here the membrane voltage is given at input to the negative terminal through a capacitor, and the positive terminal is generally reference voltage, which we have grounded in this case. So using this circuit we have received the outputs, which will be explained by my friend Praneet.
For the sodium channel gating, as you can see, we have used an FGOTA and an FG switch, and the rest all are IO buffs that are selected as pins to measure in the programming the board. So the ideal value of the sodium gating, that is VNA, should be 300 millivolts, but despite of several trials, we found out that we could not decrease the value of VNA less than 410 millivolts. Whenever there is a transition in the input, there was a spike in the output. This is basically due to the bandpass behavior of this NA channel, and the biasing values that we used were, for the FGOTA we used I bias as 1 microampere, P bias as 8 microampere, N bias as 1 microampere, and for the FG switch the I bias values were 10 microampere.
For the HH neuron, here we have utilized the sodium gating as well as the potassium gating circuit that we have seen previously. The input is provided through a OTA whose negative terminal is grounded here, and in the positive terminal we give a step input of 1 volt. So through all the processing that we have seen through sodium gate and potassium gate, we get an output here. For the output we have used an OTA buffer block to improve the quality of the output.
That we found out in the previous video, we tried to model our HH neuron using those values. If you can zoom into the picture, here we have used the HH neuron block, and we have used the ARPGen as for the input voltages for different values of Vin, ENA, EK and Vref, and the outputs were collected in this manner. So if you can see, these are the biasing values that we have given. These are the different values that we found out from the previous experiments. But in spite of giving different values and tweaking all the values, the output that we got was just a rail voltage, that is 2.4 volts. We tried it on remote test as well as the board, but still we were getting the rail voltage.
So that's all from this week's project. I am Animesh.
And I am Praneet.
And on behalf of our third teammate Hardik, thank you for watching.